For lesson 14, this section is called Graphing Factored Polynomials. We're going to start with example 1. So on page 75, you see the opening exercise. We're going to skip that for the sake of the video. We're going to skip page 76, and we're going to get to generally what this lesson is about for this video, which is graphing factored polynomials. So we look at what we have in example 1. It says graph each of the following polynomial functions. What are the functions zeros, counting multiplicities? What are the solutions to f of x equals 0? And what are the x-intercepts of the graph of the function? How does the degree of the polynomial function compare to the x-intercepts of the graph of the given function? So we are going to look at all that. We're going to slide this over a little bit. And we'll put this over here. And so if we were to solve this one, right, like we did in the previous sections, we start talking about this, we would separate each of these along here, and then we would set each one equal to 0. So we would say x equals 0, x minus 1 equals 0, and then x plus 1 equals 0. So that means this one's done. If we solve for this one, that means x would equal 1. And if we did this one, x would equal negative 1. So really, this is where we just define what we have. If we want to know what are the functions zeros, right? So we could label that down, zeros. They would be at negative 1, 0, and 1. Those are the things that make each one of these pieces go to 0. If we talked about the solutions to f of x, the solutions are the same thing. Negative 1, 0, and 1. If we said the terminology x-intercepts, well, lo and behold, that is the same thing too. So whether we call it zeros, solutions, or x-intercepts, they give the same result. And it says, how does the degree of the polynomial compare? So the degree of this polynomial is a third degree. So this is a third degree polynomial. We would know that because if we multiplied these together, we would end up with something with the largest degree of x to the third power. So the third degree tells us how many solutions that we expect to have. And so we can see 1, 2, 3. Now, in terms of graphing, right, we're just going to plug these in. So we took a blank graph paper that was in your book. We put a y-axis and an x-axis. And because we have negative 1, 0, and 1, I spaced out. So just to make a note, this one is serving as my 1. This is serving as 2. This is serving as negative 1, and this is negative 2. So we plot our points, right? We have a x-intercept or a solution at negative 1. We had a solution at 0, and we had a solution at 1. Now, for these purposes right now, this is merely a sketch. So if I was to sketch, right, I would start by going up. I have to go through this x-intercept. I don't know how high I have to go up yet, so I won't go up much. I come down through this x-intercept, and then I go back up through that intercept there. And so that's pretty much what we're looking at right now, is similarities in cases that make this work. Now, for the purpose of demonstration, I'm going to bring up a program called Desmos.com, and we could type this in. We could type in x, and this is needed, transforms as you type. So we type in x minus 1, and then we type in x plus 1, and this is the graph that we see that we would get, which is very similar to what we drew as a sketch by hand. So again, this is Desmos.com. I'd recommend you try it. Pause the video, try and type this in, see if you can make it work. If you press a little wrench, the projector mode makes it look nice. And so that's just something to note as we go forward. So now if we looked at the next part of example 1, part B, they give us another one. So let's say we just slide this over, give ourselves some room to write. We see a bunch of x plus 3's. Now we've talked about multiplicities, so that means for my zeros, right, if I write that down, my zeros, I expect to be x equals -3, and we'll say with a multiplicity of 1, 2, 3, 4 times. So a multiplicity of 4. That means the solutions is the same. That means the x-intercepts are the same. So it doesn't matter whether I call it zeros, solutions, or x-intercepts. It ends up being the same. The degree of this is 4. Number of solutions that we got represents the degree of our polynomial. So now if we were to draw a grid, right? So maybe I just draw a line across here. I draw a line across here. And we're talking about having to get to 3. So perhaps we'll just go every 2. Let's see, let's switch to this. So 1, 2, 3, 4 on this side. 1, 2, 3, 4 on this side. We'll label this 1, 2, 3, 4. Same thing on the other side, just negatives. And so the only solution that I have is -3. It's the only time it crosses the x-axis. So oddly enough, my sketch is going to actually have to come down like this. It's going to approach, and then it's going to go back up. It's never going to actually cross the x-axis because there's not another point to allow it to do that. Again, we'll model this. So if we typed in x plus 3, and we do it 4 times. So here's another x plus 3. Here's another x plus 3. We can see this is off to the side, so we can slide this over. And if we put in another one, x plus 3, there's the shape that we're looking for in part B. Alright, so let's see. Let's look at our next graph. We've got one that looks like this. We'll slide this over. If we were to talk about our x-intercepts, right, or we'll just kind of combine this, x-intercepts, solutions, and zeros. They all mean the same thing. So what we would get x equals 1. We would get x equals 2. We would get -3. And then we'll get a pair of -4's that have a multiplicity of 2. So that's what we're looking at. So we're going to draw a little grid, right? Let's see, we put a line here for our y-axis. We put a line here for the x-axis. Right there. Make that a little bit nicer. And we can, so we gotta go to -4, we'll just go every 2. So 1, 2, 3, 4. And I like to go one more pass, what my answers are going to be 5. And then 1, 2, 3, 4, and then 5. Right, we could label that 1, 2, 3, 4, 5. We know the same as on the opposite side. So if we graph these, we had a point at 1, we had a point at 2, we had a point at -3, and we had one at -4 that is a multiplicity. So if we had to predict a graph, right, maybe we're coming up this way, And since this is a multiplicity, we're not going to actually cross it. We're going to come up and we're going to touch it. Come back down a little bit. We got to go up through this one. I don't know how high, but we'll just go up some. We'll go down through this one. And then we'll go back up. Now, do I know this is exactly what the graph looks like? No, of course I don't. Do I have a good idea? Yeah, probably. How am I going to confirm and check? Same way that I showed you the last two examples. We're going to go to Desmos.com and we're going to type it in. We're going to type in x minus 1, x minus 2, x plus 3, x plus 4, and x plus 4. And we get a graph that looks like this. We'll make sure everything's typed in correctly because I can't see, so I can move this out. Let's see, x minus 1, x minus 2, x plus 3, x plus 4. Yep, it's all there. And so if we zoomed out, we can see our whole picture. Oh, see, there's more to our picture right there. Oh, look at that. If we zoom out, wow, it goes way up there, doesn't it? So in this case, right, if it goes way up there, what I can do, if I want to get a better picture, is I can change my scale. Like, for example, for my x-axis, I know I really don't need anything past -5, so I could put that there. And I don't need anything to the right of 5, so that makes that look nicer. And then I can maybe change this to -50, and maybe let's see how high I gotta go. Maybe we gotta change this to 125, and that looks like that gives me a nice picture. Now again, you should try that. You should try pressing the wrench. You should try changing your x parameters for the x-axis and your y parameters for the y-axis, and see if you can make your graph on Desmos.com look as nice as this particular image here. So one more for example 1, letter D. They give us this one, and so my solutions, right, my solutions, x-intercepts, zeros, is going to be x equals 2 and 3. Let's talk a minute about this other one. It says x squared plus 1, right? This one right here. If I tried to solve that one for 0, so if I said x squared plus 1 equals 0, and I move this over, I would get x squared equals -1. And if I tried to take the square root of -1, it's going to tell me no solution, that it is not possible. So this one ends up being something that's not part of our answer. However, it does count the fact that this is going to be a 4th degree. So we do have a 4th degree polynomial. And again, you can achieve that by multiplying these together with distributive property or tabular area model, but we're not focusing on that in this lesson. And so we could draw a line straight down, right? We can clean that up a little bit. We can draw a horizontal line across here. And if we marked out, so just 2 and 3, so maybe 1, 2, I'll do it every 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. You can always choose your own scale. Remember that. 1, 2, 3, 4. You got the same on the other side. It's always good to mark the other side a little bit, and so on. So we mark a 0 at 2. We mark a 0 at 3. This is where we can go in and out. So we would expect something to occur like this in our picture, right? You might have drawn something like this. You might have said, oh, well, that's probably going to look something like this, right? And that would be expected to be drawn by a student trying to draw a sketch of this, and this would be acceptable. How do we improve our picture at this point? Well, we would have to use a graphing utility. And so let's see how we did. We could type in x squared and then plus 1. And then we type in x minus 2 and x minus 3. And we get this funky looking shape like this. Now, one I didn't mention, if you click on the actual image, it'll show you where it crosses the x-axis. I can even find out where it crosses the y-axis. I can find other points of interest as well. And then I could even trace a point along here if I want to know more specific points. And so those are just additional features here in Desmos that relates to what we are looking at in this design. So again, this is just a sketch. Remember, and I can't emphasize that enough, these are just sketches. If I was grading a graph like this, where would I be interested at to make sure the x-intercepts are in the right place? And then you could, of course, solve for the y-intercept if you want by plugging in 0 for all the x's and see what you get for y equals. That could improve your graph feature as well. Let's look at example number 2. It says, consider this function. It says, use the fact that we know that x minus 4 is a factor of this function in this polynomial. So they're saying if we know it's a factor, that means we know that we can divide. So we could take this x minus 4 right here, and we can divide it into our polynomial to find out how many times it will divide. So we do x into x to the third, we would get x squared. We do the distributive property, get x to the third minus 4x squared. Put a minus sign. Negative 13 minus negative 4, that will end up being 9 x squared, negative 9x squared. We bring down the 44x. X goes into negative 9x squared, negative 9x times. So we get negative 9x squared plus 36x. So we put a parentheses and a minus sign, and 44 minus 36 is going to be 8. So we have an 8x, and we bring down the 32. X goes into here 8 times. So you get 8x minus 32, and there's my 0. So what do we conclude from that? That I end up with x minus 4 and an x squared minus a 9x plus an 8. Those two things multiply. They multiply to give us this function. So we're trying to reduce it and find the x-intercepts. So I can take and I can factor this one by writing x and x. We could put a minus 8 and a minus 1. Again, how do I know that works? Because if I do this one, that gives me negative 8x. If I do this one, I get negative 1x, and they add up to equal negative 9x, which is what we're looking for. So now I can factor, or solve for the x-intercepts. I can set each one equal to 0, so I can say x minus 4 equals 0. I can say x minus 8 equals 0. And I can say x minus 1 equals 0. So that means I get x equals 4, I get x equals 8, and I get x equals 1. That is my results for my x-intercepts. In C, they say, at which x values can the function change from being positive to negative or negative to positive? And what they mean by that is if I had a graph, let's say I had this line and this line, every single time, so this is how this works, every single time I go from, say, a negative y value to a positive y value, I have to change where I am on the x-axis. I have to cross the x-axis to get from negative to positive results. So at which x values can it change from being positive and negative? We have to say the x-intercepts. This is one reason why we look for those particular x-intercepts, to take advantage of that. It says in D, to sketch a graph of f, we need to consider whether the function is positive or negative at each of the intervals, from less than 1, between 1 and 4, between 4 and 8, and then greater than 8. That is because, remember, we said that our x-intercepts was 1, 4, and 8, right? Let's go back and see that. 1, 4, and 8. So if I thought about this on a number line, right? So let's say we draw a number line just to illustrate this point. If I had my x equals 1 here, if I had 4 here, so let's say 1, 4, and 8. There are different regions. For x is less than 1, that's all of this space right here. For between 1 and 4, that would be all of this space here. For between 4 and 8, that would be all of this space. And for everything greater than 8, that would be everything over here. So there are 4 regions that I can examine. So E asks, how can we tell the function is positive or negative in between these x-intercepts? Well, we can pick a number in that interval, plug in for x, and get a positive or negative y value. So that is what we're going to do. So let's say for x is less than 1, right? Let's say I choose, let's use a different color. Let x equal, let's just say 0, right? 0 is less than 1, so we're going to put into our equation y equals 0 to the third power minus 13 times 0 squared plus 44 times 0 minus 32. And we calculate that, and we find out that y is equal to negative 32, which is negative. So we're going to just remember that. Let's say we choose something between 1 and 4. Let's say we choose 2. Let x equal 2. So then we have y equals 2 to the third power minus 13 times 2 squared plus 44 times 2, and then minus 32. Right? I'd recommend you just grab a calculator for that, and I'm going to do the same thing. So we'll type in 2 to the third power minus 13 times 2 to the second power, which is 4. And then we're going to add that to 44 times 2. And we're going to minus 32. And we're going to get a y value that is equal to 12. So that's going to be positive. Let's say we look at the next one between 4 and 8. Let's say we let x equal 6. So that means I'm going to put y equals 6 to the third power minus 13 times 6 squared plus 44 times 6 and then minus 32. So again, go to a calculator. You do 6 to the third power minus 13 times 6 squared, which is 36, plus 44 times 6 minus 32, and we're going to get y equals negative 20. So again, we get a negative value. And then for the last one, let's say we just say x is equal to, let's just go with 10, something bigger than 8. So we have 10 to the third power, right? Let's write y equals y equals 10 to the third power minus 13 times 10 squared plus 44 times 10 and then minus 32. So 10 to the third power, which is 1,000, minus 13 times 100, which is 10 squared, plus 44 times 10, and then minus 32, and we're going to get y equals 108, which is positive. Now notice this trend. This is something interesting to look at. We did not have any multiplicities, and in this case, notice we had negative, then positive, then negative, then positive. So that's an interesting thing to note and observe. So we're going to try to graph this, noting what it is that we see. For each one, we're going to draw a sketch. So remember, we need an x-axis and a y-axis, so we'll put that on there. Here's an x-axis. Here's a y-axis. And we had things at what? 1, 4, and 8. So we'll just go, let's see. We'll just go 1, 2, 3, 4, 5, 6, 7, 8. We'll just go by ones this time. And then 1, 2, 3, 4, 5, 6, 7, 8. So that means I'm going to put a dot. We said one of my x-intercepts was 1. One of them was 4, so 2, 3, 1, 2, 3, 4. And then 5, 6, 7, 8. So remember, we had this pattern that when we were less than 1, for x is less than 1, we were negative. When x was between 1 and 4, we were positive. When we were between 4 and 8, we were negative. And when x was greater than 8, we were positive. So we can use that information to better draw our lines. So we know we had to start at the bottom, negative territory. We come up. We're in the positive territory. We have to come back down. Now we're in the negative territory. And we come back up. And we're in the positive territory. Right, so that's our graph. It says in part K, graph on the interval from 0 to 9 using a graphing utility and compare it to what we did. So to wrap this idea up, we go to our Desmos, right? We could type in our graph. They said to go from a window from 0 to 9. So we can go ahead and set that 0 to 9 for the x-axis. We'll adjust the y-axis in a minute. But our equation was x to the third power minus 13 x squared and then plus 44x and then minus 32, right? So we see our graph. We can zoom out if we want to see it better. and we see what our graph is doing. We can see the similarities. So like if I went back to here, you can see this one and this one are similar in the way that we designed our given graph in that perspective. Alright, so that's where we're going to end this video. Take a look at the problem set, and then of course let me know if you need any additional support.